And yeah, we'll go over them. Let's talk about those questions. So far on your GDT stuff, you're learning the dimensioning things, a lot of information out there. Any questions on quiz material you want to ask? Okay, what is number one?
Still, there's a hole in there.
Yep. Okay. Okay, so let's talk it through. So you've got a hole in a plate of steel, and the condition associated with this is called MMC. What's MMC stand for? Most or max, most material condition, right? Which either way you say max or most doesn't matter. It's MMC means most material, max material condition. So if we're talking about a hole, logically, does a big hole or a small hole end up being most material? The small. Why is that? Because if I have a hole this big, that's one thing. If I have a hole this big, that's another thing. Whichever one leaves the most steel, that is the most material, because there's more material left over, right? Does that make sense? Now, is that the exact same logic for perhaps a cylinder going in that hole?
Yeah.
Exactly. It'd be the opposite, right? So, most material condition for a cylinder would be a big cylinder versus a small cylinder. Makes sense, doesn't it? Now, what you have to understand why that's important in GDTs is because you're going to start seeing GDTs on plans with this symbol in the feature control frame. And sometimes it can pop over in one of the reference blocks. It can sometimes pop up in the size of the tolerance zone, whatever the case may be. But here's what you want to take away from this. First of all, you do need to understand which way it goes if you're dealing with a hole versus a solid object. But second is, this is actually a good thing to see on a set of plans. Here's why. If I give you a part and I say 7.7 plus or minus 1, that's a tolerance, right? And if you're in quality control, no matter what happens when that part comes through, you have to reach down and check with your tape to make sure that fits within the range, correct? So you have to make sure that it's either 8.7, no higher than that, or 6.7, no lower than that. You got to check every single one, right? Well, the good news about when you see this M or L in a circle, it gives you an out. It means you don't always have to check. Here's what happens. So here's a hole being drilled in place, and let's say its diameter is 10 plus or minus 1. And I give a feature control frame right here that says position tolerance and diameter, I don't know, diameter 2, and it's got an M in it. Okay? What does that mean? It means that you can ignore this feature control frame when the M doesn't happen. Okay? So let's focus on this for a second. So with this number system, with this hole size, right? You can have a diameter that is diameter 11 and it passes, correct? You can have a diameter of 10 and it passes, right? But my question to you is right now, which one of these two values is the MC condition? The 9 or the 11? Just the 9, right? Yep. So technically, only when this hole is on the small side does the M condition exist. Which means only when we're on the small side of this do you have to pay attention to that. Does that make sense? Do it. The M is the MMC, yes. Yeah, MMC and equals the M in a circle. So when you see one of these modifiers in a feature control frame, your first thought is, well, wait a minute, I don't actually have to check this every single time. I get to check this when certain conditions happen. So do I still have to check the circle? Yes, I still have to put a measuring tape to it and see that it came out to either 11 or 9 as my extremes. But if it comes out as 11, do I actually have to check this feature?
I don't think so, because you're getting at your limit.
But the limit doesn't matter in this case. Keep in mind, this modifier right here tells you when you have to check.
Yeah, if it's 11.
No.
I mean, you were asking if it was 11.
If it's 11, 11 is not the M condition, is it? Which one of these measurements is the M condition? 11 or 9?
Well, the 9. Yeah.
The 9. So if 11 is not an M condition, then should I have to check this? The answer is no. You only have to check a feature control frame when it has one of these in it. Now, don't get me wrong. If this isn't in there, you check it every time. But when you see one of these modifiers like M or L, it tells you I don't always have to check this tolerance. Now, I'm not talking about this tolerance. You always have to check it. I'm talking about this tolerance. So then you have to ask yourself, well, which one of these two measurements, 11 or 9, actually results in the M condition? It's the 9 that results in it because that's the most material condition. Therefore, then I have to check this. If it turns out to be an 11, if I measure the circle at 11, then I don't have to check this.
Okay, where I'm getting mixed, or where I'm getting, I guess, mixed.
You don't actually, this M doesn't tell a person to do something. It's not something you're shooting for. This is saying, check this if. Okay? We're not going after you all actually creating MMCs or LMCs. We're just saying if you measure this hole and it ends up being on the small side, which causes an M condition, then you need to check this. If you go in and you measure and this hole is large, so therefore it is not an M, then you don't have to worry about checking this thing. So you get to basically, by saying this is not an M, means you don't have to worry about this now.
I see what you're saying.
Next part that comes along though, let's say the next part that comes along ends up having a small hole. And you check this. It does pass quality control, or it does pass tolerance, but it also ends up being a small hole, which is an M condition, which means now I have to turn around and check this condition. So that's one of the nice things about it. Okay? Keep that in mind. One thing you got to keep in mind is the fact that those M and L's, least material condition. So, and we'll go into a little bit more detail on that. They basically mean that you don't always have to check all of these. Keep in mind, we're talking about two different types of tolerances too. This plus or minus down here is a tolerance, but that's a normal tolerance. That's the stuff everybody understands. This one, this feature control frame, is a geometric tolerance. A lot of times you have to check them every single part. Sometimes when you get these suckers, then you don't always have to check it. Mm-hmm. So that's what these modifiers are standing for. They give you an out in terms of testing. Okay. Now let's go with that question a little bit more. So an MMC is equal to this symbol on a set of plans. An LMC is equal to this symbol on a set of plans. So if I am drilling a hole and I have a tolerance of +1 and a tolerance of -1, which condition on this hole is an LMC? Okay, so let's think it through. And LMC means least material condition. So it means if I'm drilling a hole, I'm talking about a big hole, right? So that means that it is yes on the high side of the tolerance. So there is my L. Okay. Now again, it's flip-flopped when you're dealing with a cylinder. That's when you're drilling a hole. When you're dealing with a cylinder, that means that it would be opposite. So if I was making a cylinder and it's a +1, then I have a most material condition. See the difference between the two? It's all about how much material is left. It's all about how much steel, if you think of it that way, how much steel is represented. Think about it for a second. See if it processes. See if it clicks. If it helps, here's what I do. I draw a picture. So if I'm thinking MMC or LMC and I draw a cylinder, I'll think big cylinder, small cylinder. Big cylinder gives me an M. Small cylinder gives me an L, which means that I was on the high side of a tolerance or on the low side of a tolerance. I'm drilling a hole. Big hole gives me an L or M. An L. Little hole gives me a what? An M. That's the way you kind of back and forth the process. Okay? Questions on that? All right. Give me another question. What else you got? Okay. Which is? Okay. What is chain dimensioning? Okay. So chain dimensioning. What is it? What can you tell me a little bit about it? If it helps, we can always draw a picture.
You're going from one point to the next.
There you go. You're going from one feature, one point to the next. So this would be an example of chain dimensioning. Dimension there, dimension there, dimension there. It's a chain. Yeah, you've seen it. You've seen it a lot of times. We talked about it, but that's what chain dimensioning is. But what's the drawback with doing this? The measurements, your tolerances get added up. So I've got a plus or minus here, a plus or minus here, a plus or minus here. So every little area of tolerance here, every little area of tolerance here, every little area of tolerance here ends up making the overall part have a lot of error. Because you're allowed tolerances. You can be off a little bit. But let's say that you're short on this one, short on this one, short on this one. You're still okay because tolerance is okay. But what does that do with the overall length of the part? It all adds up to a big bunch of shortness, right? That's right. By a whole bunch of little mistakes adds up. So chain dimensioning is done that way. Now, what's the opposite of chain dimensioning? Datum. So how do we do that? Well, datum dimensioning, pretty straightforward. You pick a datum. One edge of a surface is pretty typical, or maybe some node or something. You measure to here. You go back to that datum. You measure to here. You go back to that datum. Even though it's on the bottom, I'm still using the same datum. You measure to there, and then you go get the overall length of the part to there. You can call it the base point of origin. In technical terms, you're creating a datum. So this surface itself is considered a datum. But if it's a base point and you think of it that way, that's fine. Origin, you think of it that way, it's fine. But in GDT terms, we would identify this as a datum. And don't forget, if I want to identify a datum, I typically will add that little symbol right there to establish it as being a datum. So definitely clear on why we have less error here. They don't add up. You make a mistake on this one, has no impact on this one. You make a mistake on this one, has no impact on the overall length. So that's the kind of way it works out. This is why your drawings and blueprints, more advanced versions of them, will always work off a datum. Next question. Yep.
Oh, I was just going to ask.
Yep.
What would be a scenario where they would use chain over datum?
Okay. Not so much in fabrication, but in architectural work. I'm building a big building. Steel frame, steel fabrication, where we're building steel frames and those kind of things, where you can't actually go from the outside of a building and measure everything. They're going to go from wall to wall to wall to wall. Yep.
I was kind of wondering why anybody would pick it over the other one.
Yep. Size is the driving factor there. Even if you got into large steel fabrication, they could be doing okay with chain. But datum is actually faster to fabricate with. I mean, you think about it, you put your tape down on one end and you just keep measuring. Otherwise, you would be trying to measure off the center of a hole to the next hole. So it's just faster typically.
And if you can, say you're going to measure with a ruler or whatever.
Yeah.
If you can, like you said, if you can, once you start, don't move that ruler and mark a.
Right. If you've ever seen him, and even in architectural, if you've ever seen anybody lay out a wall frame, like a wood wall frame, they will take their measuring tape and they'll stick it on the end and they'll take their tape down and they hit 16, they hit 32, They hit 48, they're going to actually technically do a datum dimensioning format, even though they're in the architectural field. But they're dealing with like a wood stud or wood wall when it's easy to measure that one time. But that keeps their accuracy high. So like if you ever help anybody frame up a wall, that's the best way to lay out the studs. They're going to do that, then they're going to draw, say a speed square, draw a line, put an X, speed square, draw a line, put an X, speed square, draw a line, put an X. And then they'll know where to frame their stuff. Then they're going to get another stud that matches up with it, transfer the lines, and then they'll have two ends of the wall to actually put the studs in and frame it up and that kind of thing. So, datum dimensioning. Next question. Well, give me the synopsis here. What do we need to know about?
Let's talk about what I guess a normal tolerance would be if you was locating the center point.
Okay, so your target is you're concerned about the location of a center point of a drilled hole, and you're very concerned about it. What GDT would you all say is a good call to use on this situation? Well, that's a size. I was asking what type of GDT to use.
I thought cocentricity.
Okay, well that's in the right direction, but cocentricity is actually based on multiple circles, so you can't use that one.
Yeah, you're right.
Give me another option.
I put true positional on.
You are correct. True position is the one that you want to use on that one. Because true position is all about true position, a point in space. Now, the tolerance itself, the size of the zone, that's up to a person. And by the way, that also answers this question too. A true position typically has a circular zone. So let's say that you set the tolerance zone to be 1, it's going to be a diameter space. So that means the center could be there, there, or there, and still passes. What happens if the center point ends up being out here? Does it pass? Right. So this little zone that I just drew technically is the diameter 1 of our tolerance. We're calling out a true position, which means it can be, that center point can be anywhere in this, theoretical perfect and be fine. And that's how we would control. Connects now, right? So that's why we do these quizzes. So
I'm like Eli. I knew what we was talking about, but I just wasn't sure what.
it's okay. That's why we throw it up on the screen for you to see an example of and for it to make sense. Now, so that also answers the other question of what type of zone is a true position typically. What kind of tolerance zone shape is it in? What kind of shape's that? Right here? Circle. Most of them will be there.
That one confused me because I can find it.
Yep.
I was reading through the packet while watching the video, and on one of the figures at the parts, I put square on mine.
Well, that is true. That some cases they can actually square the zone.
Yeah.
It's just very rare.
Yeah, because this one right here, the figure uses the square. So
Yeah.
I put square on mine.
And that's understandable. I mean, there is a case for it. That's why I was trying to go for the typical side.
Yeah.
Most of the time on set plans, you're going to see it done with a zone versus a square. Now, why is that? Well, it's because it knocks, so I don't know necessarily this is the exact reason, but you get a little bit more flexibility with a circular, or it's a little bit easier for people to check that zone with a circular tolerance zone versus a square tolerance zone, because it's harder to tell if this thing's in or out the right areas on these corners. But most of the times on plans that I've seen especially, you're going to have a round circular tolerance zone. But it's okay. We're still learning. Another question.
That's what made me think circular was not.
Well, it does have a case for it. There's a case. But you're going to see in practical results, you're going to always see pretty much a circle. No one really actually tries to check with a square that I've seen on set plans. All right, another question. But you had a good reason for being off on that answer, so that's the best part. You had data that said, no, wait a minute, right here in this diagram, it shows it being a square. So that's good documentation. Yep, next question. Well, it wants you to call out the tolerance. All right, so read off 5 to me. Okay. So in essence, in the feature control frame, you were actually responding to this part of it, like the tolerance size. What I'm asking for is what goes in this box. So what goes in this box for that question? What geometric tolerance deals with surfaces that would be aligned to each other, or AKA parallel with each other? Not that one. When in doubt, you can always go to the packet and check your chart. There's one, actually I was trying to struggle with giving you the word parallel because I was going to give it away. Look down the chart. Look down on your chart. It will jump out at you. Oh, parallel?
That's actual, parallelism is the actual name.
Yeah, parallelism is the actual name of the GDT. So if you want two surfaces to be aligned to each other or parallel to each other, you use this tolerance, parallelism. What it essentially means is this: if you have a part and you want this surface to be parallel to this surface, for example, let's number them here, 1, 2, 3, 4. If I want surface 2 to be parallel to 4, the feature control frame would have to involve the parallel geotolerance. It'd have to have a zone, so let's just give it a zone of 1.0, and it would have to have a reference, right? We have to tell the viewer or the viewer has to understand that surface 2 needs to be parallel to some surface, some controlling surface. So what surface is that? 4. So I have to establish 4 as being the controlling surface. So I do that by adding one of our datum symbols right here. And I put that down. But I have to turn around and link that back to this one so they know which one to check. So what goes in this box right here? A. So there's 2 parts to this process. Now the question didn't require you to do all these parts. It just said, hey, what type of geotolerance would you use? But you have to establish which one's the controller. That would be the datum. You have to establish the type of tolerance you're going to use. You have to establish the zone size, and you have to tell it which type of data or which datum you're going to reference. So I have to identify that 4 is the actual one I'm referencing by saying, okay, there's my A, I look on the plans, here's my A, so that means that 4 is the one that's controlling the whole thing. Side question though, could surface 1 and 3 actually be used with this geotolerance? No, because they're not parallel at all to 2, right? Now, what also can you tell about this part by the fact that I've given this GDT to it? Which is the most crucial surface of this part? Well, that's a good point, because it's the controller. But in reality, what's actually needs to be checked? 2. So whatever this part is used for, 2 is whatever its function is, it's important. Now you're right, 4 has to be there. 4 is very crucial because you have to use 4 to make 2 compared to, right? So I get your point there. You know, you've got a good argument there. But that's, I'm just trying to drive home the fact when you're looking at said plans, these things tell you what's crucial. You should be looking at a part to understand what's important about it versus other features so that you can make good decisions on it. Got another question? Any at all? Yep.
I somehow totally didn't answer that question as I'm coming up.
Thing is that you had your documents out, your reasoning, and you're using logic to make some of the decisions. Like even going back to that square thing on the zone, there is a case for it. And there's always exceptions to the rules, and the fact that you can pull up some documentation to support that, that's good on your side. Now, any questions you want to ask on the homework that you are currently working on and getting ahead on, so you're not crunch time at the very end and overwhelming yourselves. So that'll be a good breaking point.